4. I am going to explain you unit 4 short answer questions. Here first one is a D flip-flop truth table and logic diagram they asked. This is a D flip-flop logic diagram using NAND. This is the input and this is the clock pulse. These are outputs. Then the clock D, Qn prime state, Qn plus 1 next state. So here D is a single variable. We have two cases. When D equal to 0, what is the output? When D equal to 1, what is the output? If D equal to 0, if I am taking D equal to 0, maybe prime state is 0. D equal to 0, prime state is 0. Output will be 0. If you substitute here 0, you will get next state as 0. Similarly, same D equal to 0. For example, my prime state is 1. You will get output 0. Nothing but whatever it may be the prime state, D value will get as output. D is 0, output is 0, or Qn plus 1 is 0. Similarly, if D equal to 1, prime state is 0, output is 1, prime state is 1, output is 1. Nothing but whatever it may be the prime state, output is same as the D value, nothing but D and Qn plus 1. In short form, D is 0, output is 0. D is 1, output is 1. This is the shortcut manner. Irrespective of prime state, output is same as the D, delay flip-flop. Data, whatever we are giving, that is we are getting same as the output. And similarly, go to fifth question also. Otherwise, we will explain later. Second question is the serial in, serial out shift register. Serial in, serial out shift register. I am taking a 3-bit register. If you want, you can take 4-bit register. In the textbook, we have 4-bit. D1, D2, D3, D1, Q1, Q1 bar. This is the first flip-flop, second flip-flop, third flip-flop. So here serial in, serial out shift register is nothing but I am taking 3-bit. So clock is connecting simultaneously to all flip-flops. This is a synchronous counter. And I am giving data as in serial manner. Serial data, serial input. We are giving, for example, 0 will give, it will shift to D2, it will shift to D3 and so on. So data we are giving serially, it will shift and output we are getting in serial manner. This is serial in, serial out shift register. For example, I am giving 0 input and applying clock signal. This 0, if D equal to 0, what is the output? If D equal to 0, what is the output? 0. So output will be 0. For the first clock pulse, output is 0 dash dash. Why? Because these 3 bits are not having output. Next I am giving 1. I am giving serial input 1. So this is the input for the D2. This output is 0. Here I am giving input as 1. Here the output is 1. Again here there is no output. Again I am giving 0. So this 0 will come as output. D, whatever the input you are getting, output as 0. Output as same. Here input is 1, output is 1. Here I am giving input 0, third bit 0 will get as like this. So now the last bit is 0. This is the serial out. Okay, this is serial in, serial shift register. Here parallel in, parallel out also they are mentioned. Just go through the diagram in the textbook. Then third question is ring counter. Only small change is the output directly connecting as the input of the D flip-flop. The last flip-flop output is connecting as the input of the first flip-flop. That is ring counter. Okay, that is the only change. Similarly, fourth question, JK flip-flop excitation table. What is excitation table and explain the JK excitation table. So excitation means state change. From one place prime state to next state. And that time what are the corresponding flip-flops. So that is excitation table. State transition or changes with respect to the flip-flop inputs, that is excitation. For example, I want to write JK flip-flop excitation table, and this is the reverse of the truth table. First you can write a truth table, JK Qn plus 1, prime state, next state. For 0 0, output is 0 comma 1, and for 0 1 0, for 1 0 1, for 1 1 you are getting like this. If j equals 0, k equals 0, prime state is 0, next state is 0. Similarly, j equals 0, k equals prime state to next state is 1. This is no change state. This is the reset state. This is set state. This is toggle state. This is already you know. How you can write excitation table from truth table. We are going to see excitations are from Q1 to Qn plus 1, prime state to next state, 0 to 0, 0 to 1, 1 to 0, 1 to 1. These are possibilities of excitations, 0 to 0, 0 to 1, 1 to 0, 1 to 1. I am checking prime state to next state. If 0 to 0, what are the corresponding JK? 0 to 0 corresponding JK I am checking. J value is 0, K value is 0. 0 to 0, K JK is 0 0 0 0. Is there any other 0 to 0s? You can verify. Here we have 0 to 0 0 to 0. What are corresponding JK? 0 1 0 1. Nothing but J is fixed, K is changing. J is 0, K is changing means don't care. 0 don't care. 0 don't care. Like that you can write. All possible cases you can write. From the truth table, prime state to next state, 0 to 0 K possibilities corresponding JK. 0 and K is changing. 0 don't care. Similarly, 0 to 1 case. 0 to 1 case. Where we have 0 to 1, you can verify. 0, 0, 0, 0 to 1. This is 0 to 1. 0 to 1. What are corresponding flip-flops? 1, 0. 1, 0. Similarly, is there any other 0 to 1s? Here we have 0 to 1. 1, 1. Flip-flops are 1, 1. Check this. J is 1, K is changing. J is 1, K is changing. 1 don't care. 1 don't care. Like that you can write. J is fixed, K is changing. 1 don't care. Similarly, 1, 0. 1 to 0 you can verify. 1 to 0. This is 1 to 0. Flip-flops are 0, 1. Flip-flops are 0, 1. 1 to 0. Last case 1 1 1 1. See here, J is changing, K is fixed. 1 don't care. Don't care 1. Don't care 1. Don't care 1. Similarly, you can write for 1 1. You will get don't care 0. K is fixed, J is changing. This is the excitation table for JK flip flop. Similarly, another question they gave for T flip flop also you can write excitation table. You can verify that. Similarly, fifth question is SR flip flop truth table. SR flip flop truth table. This is SR flip flop. This is R. This is S. This is SR flip flop logic diagram. In between S and R, if you keep NOT gate, that is D flip flop. So here you can write first 3 states are same for JK and SR. 0 0 no change state, 0 1 reset state, 1 0 set state, 1 1 indeterminate state or invalid state. That is about fifth question, SR flip flop. Okay, next go to sixth, 2-bit ripple counter, ripple or asynchronous counter. Okay, for the first flip flop we are going to give the clock signal, clock pulse. First flip flop we are going to give the clock signal, and T input I am taking as 1. 2-bit, that is why I am taking 2 flip flops. 2-bit ripple down counter they gave first. So this is the first flip flop. The first flip flop outputs are Q1 and Q1 bar. If the Q1 bar acting as the clock for the next flip flop, that is down counter. If Q1 is acting as the clock for the next flip flop, that is up counter. 2-bit ripple counter, T1, T2, 2 flip flops. And ripple means first flip flop only are giving the clock. First flip flop outputs are acting as the clock.